Hello everyone and welcome to our new section which is called graph algorithms. A graph is a nonlinear data structure consists of nodes and edges. The nodes are sometimes also referred as vertices and the edges are lines or arcs that connect these two nodes in the graph. More formally, a graph can be defined as a graph consists of finite set of vertices or nodes and set of edges which connect pair of nodes. Now let's see what we mean by vertices and edges. So here, the circular objects that we show over here, which are A, D, B, K, J, E, are the vertices, and the lines that connect these circular objects are the edges. So from here, you see that these are nodes or vertices, and these are the edges in our graph. So hopefully with this typical graph picture, you have understood the definition of graph data structure. Now let's see why we need graph data structure. Graphs are used to solve many real-life problems. Graphs are used to represent networks. The networks may include paths in a city, or telephone network, or circuit network. Graphs are also used in social networks like LinkedIn, Facebook. Now let's say we are given a problem called shortest path between cities. So here we have given a map of Europe to find the shortest path between cities that are mentioned over here. And these cities are connected using these paths over here, which shows the flight from one city to another city. So here you can see that from London you have different flights to different city. Now let's say if you want to go from London to Baku, we have different paths. So we don't have direct flight to the Baku. So to go to Baku we can fly to Moscow, then come to Baku, or we can fly to Kiev and then come to Baku, or we can fly to Istanbul and then come to Baku. Now as you can see we have different paths to Baku from London. So the question is, how we identify the shortest path to Baku. So in this case, we need a data structure which handle this. So if we look at the data structures that we have learned till now, we can easily see that the only option is tree data structure, because tree data structure has nodes and these nodes are connected with path. Now the problem with the tree data structure is that we don't have cycle there. But here in this map, you can easily see that we have cycle over here. So for example, when we travel from London to Moscow, then travel to Baku, and from Baku we can travel to Istanbul and back to London. So here we have circular path over here. So this case cannot be handled in case of tree, because in case of tree we don't have any cycle. So the only option is graph data structure. See how can we solve this problem using graph data structure. So in a typical graph, we have vertices and edges. So we can represent these cities as vertices in this graph, and we can connect them with edge, and the edge will be the path between these cities, and we can calculate the cost of this path and set them as weight. So after doing so, we can solve the problem of shortest path. Now we are not going to solve this here because we will discuss this problem of shortest path in our upcoming lectures. Here you just need to know that by creating the graph for these cities and paths over here, we can solve shortest problem using different algorithm. So hopefully you have understood what's a graph and why we need it. Now in the next lecture, let's see graph terminology, which are very useful when dealing with graphs. So see you in the next lecture. Now in this lecture, we will learn about graph terminology, which are very useful when dealing with graphs, and it's very useful especially during the interview process. So the first terminology is vertices. So in a single formula, it's called vertex. Vertices are the nodes of graph. So if you look at this graph over here, we can easily see that these nodes that are in circular format are called vertices. So in our case, we have 5 vertices in our graph, which are V1, V2, V3, V4, and V5. Now the next terminology is edge. So the edge is the line that connects the pairs of vertices. So in this graph, these lines over here are called edges. So these edges are responsible for connecting these vertices over here. So you see that we have a connection between V1 and V2, and we have a connection between V1 and V4, and we have a connection between V1 and V3, and so on. So these connections are called edges. So the next terminology is unweighted graphs. A graph which does not have a weight associated with any edge is called unweighted graph. So in this graph that we have over here, we see that we don't have any weight that is associated with any edge over here. All edges that we showed here is unweighted, so our graph is called unweighted graph. Now in case we define any weight for the edge over here, so this graph will be called weighted graph. So here you can see that to travel from V1 to V2, it takes 8 units of time. And similarly, from V1 to V4, it takes 12 units to travel. So this means that we have weights associated with the edge, so this graph will be called weighted graph. Now the next terminology is undirected graph. So in case the edge of graph do not have a direction associated with them, then this is called undirected graph. Now let's look at this edge over here. Now we see that there is no direction specified for these edges over here. It means that we can travel from V1 to V2 and V2 to V1. So we don't have any restriction for traveling between these vertices over here. So we can easily travel from V1 to V4 and V4 to V1. We don't have any direction specified. So similarly, if the edges in a graph have a direction associated with them, we can call that graph a directed graph. So let's say we have a direction from V1 to V2. So in this case, we can travel from V1 to V2, but we cannot travel from V2 to V1 because here this is one-way traffic. So another might be like this: we can travel from V1 to V4, but we cannot go back from V4 to V1. So if we want to go from V4 to V1, we need to try another path that exists over here. Now the next terminology is cyclic graph. So in case a graph has at least one loop, then in this case it is called cyclic graph. Now what's the loop in the graph? A loop occurs in the case that, so if you leave from one vertex and come back to this vertex through other path, then we have a loop over here. Now in our case, in this graph, the first loop is like this. We can go from V1 to V2, then V2 to V4, and from V2 we can come back to the V1. So you see that we have a cycle over here. So if in a graph we have at least one cycle, then this graph is called cyclic graph. Now here the next cycle is like this. So from V1 we can go to V4, V5, V3, then we can come back to V1. So in this case we have another cycle over here. Now if the graph does not have any loop, then in this case this graph is called a cyclic graph. Now here an example, this graph is a cyclic graph because here you see that we don't have any loop. So we can go to from V1 to V2 and we can come back. We don't have any over here. And similarly, we can go from V1 to V3 and V5 and we can come back. But we do not come back through different paths. We are coming back with the same path. So in this case, we don't have any loop in this graph over here. That's why it's called a cyclic graph. Now the next terminology is tree. So tree is a special case of directed acyclic graph. So here we have a sample tree over here and we can see that it's directed. So we can travel from V1 to V2, but we cannot come back to V1, and we can travel from V1 to V3 and V5, but we cannot come back. And this is acyclic because there is no any loop in this graph over here. So a tree is a special case of directed acyclic graphs. Now with this, we have completed the terminology of graph. So you have to keep in mind that these terminologies are very useful, especially during the interview process, and we will use these terminologies very frequently in our upcoming lectures. So it's very useful to learn them from upfront. Now with this, we have come to the end of this lecture. Now in the next lecture, we will learn different types of graph. So see you in the next lecture. Alright, now in the previous lecture, we have learned graph terminologies. Now in this lecture, we will learn types of graph. So graph generally can be categorized into two categories: directed graphs and undirected graph. And in directed graph, we have two subcategories, which are weighted graph and unweighted graph. And in undirected graph also we have two categories, which are weighted graphs and unweighted graph. Now weighted graphs can be into two categories, which will be negative and positive graphs. And here also undirected graphs. In case of weighted, it can be positive and negative graph. Now if we look at this picture, we can see that we have 6 different types of graphs, which are directed weighted positive graphs, directed weighted negative graphs, directed unweighted, and undirected weighted positive graphs, undirected weighted negative graphs, and finally undirected and unweighted graphs. Now let's look at them one by one. So the first one is unweighted undirected graphs. So what is unweighted and undirected graphs? So if we look at this graph over here, we see that this is unweighted and undirected. This means that we don't have any weight that is associated with the edge of this graph over here. So all edges are unweighted, and for the edge we don't have any specific direction. So this means that we can travel from V1 to V2 and from V2 to V1. And similarly, we can travel from V1 to V3 and we can come back to from V3 to V1. So we don't have any direction that is associated with the edge over here. So if we don't have any direction, this is undirected, and it means that we have access for the both way. And if we don't have any direction and any weight that is associated with the edge, this is called unweighted and undirected graph. Now the second type of graph is unweighted and directed graph. So in this case, we don't have any weight that is associated with the edge, but we have direction specified for the edge. It means that we can travel from V1 to V2, but we cannot come back from V2 to V1 because this is one-way traffic. So here you see that this arrow specifies it that we can only travel from V1 to V2. And similarly, we can travel from V2 to V4, but we cannot come back from V4 to V2. But in this case, we have two-way traffic over here. We can travel from V1 to V4, and we can come back from V4 to V1. Here also it specifies that we have two direction over here. So that's why it's called directed graph. Now in this case, you see that we don't have any weight that is associated with the edge. So in this case, this is unweighted and directed graph. Now let's continue to the next type of graph, which is positive weighted undirected graph. Now in this case, if graph edges have edges that are associated with them, so in this case, this is called weighted graph. Now if these weights are positive numbers, so we can call it positive weighted graph. And if edges do not have any direction with them, this is called undirected. So if we combine all these property, it is called positive weighted undirected graph. So here you see that we don't have any direction that is associated with the edge. We have only positive numbers, which are weight of edge. So it's called positive weighted graph. So here we can go from any node to the other vertex and come back from that vertex to the current vertex over here. So in this case, it's called positive weighted undirected graph. Now the next type of graph is positive weighted directed graph. So this case is also similar to the third case, but here we have direction that is associated with the edge. So in this case, we can travel from V1 to V3, but we cannot come back from V3 to V1. So because here we have directions associated with them. And here all weights are positive numbers. That's why it's called positive weighted directed graph. Now the next type of graph is negative weighted undirected graph. So in this case, if any weight that is associated with the edge is negative, in this case we are calling it negative weighted graph because at least one weight is negative weight. So here you see that from V1 to V4 we have -5, and from V1 to V3 we have -3. So this is negative weighted and undirected graph. It is undirected because we don't have any direction that is associated with the edge. So we can easily travel from V1 to V3 and we can come back from V3 to V1. So we don't have any direction that is associated with them. In case we have any direction over here, it will call negative weighted directed graph. So here you can see that we have at least one negative weight that is associated with the edge, and we have direction that is specified for edge over here. So here you can see that we can easily go from V3 to V5, but we cannot come back from V5 to V3. So this is directed graph and we have negative edge, so this is negative weighted directed graph. Now with this, we have completed all 6 types of graphs. So hopefully everything is clear about these types. So these types of graph are very important during interview process because many interviewers are asking about different types of graphs. So you have to learn them very carefully. Now with this, we have concluded different types of graph lecture. Now in the next lecture, we will learn how can we represent graph in our codes. So see you in the next lecture. Alright, In the previous video, we have learned 6 different types of graph data structure. Now in this video, we will learn how can we present graph data structure in our code. Now the first way to represent the graph is using adjacency matrix. Basically, an adjacency matrix is a square matrix, or you can say it is two-dimensional array. And the elements of matrix indicate whether the pairs of vertices are adjacent or not in the graph. So let's say this is our graph, and we can easily see that this is an unweighted and undirected graph. So this means that A is connected to B and B also is connected to A. Since we don't have any direction over here, we can easily say that B is also connected to A. Similarly, C is connected to D and D is connected to C, and it continues like this. So how can we represent this graph using adjacency matrix? So here the first step is we create two-dimensional array with the size of number of vertices in the graph. So in our graph we have 5 vertices. So as you can see, A, B, C, D, E are the vertices, so the number of vertices are 5. So this means that we will create two-dimensional array 5 to 5. And when we create 5 to 5 matrices, we initialize all elements of two-dimensional array to 0. Then the next thing that we are going to do, we have to plot these edges that we have over here to this two-dimensional array over here. So we will start from each vertex and see that to which vertices they have connections. So we will update this matrix over here. So first we will start from A. So from A we see that we have a connection to B. So this means that we will update AB to 1. Then the next connection is from A to C. So this means that we will update AC to 1 also. And from A we have another connection which is to D. So in this case we will update AD to 1 also. Now we have finished with A, we will continue to the B. So from B we have a connection to A and E. So this means that we will update BA and BE to 1. So here we are updating these cells to 1. So as you see, in each cell we have zeros from A to A and from B to B and from C to C. This represents the diagonal over here. So this means that from A to A we don't have any connection. So for all vertices we set all them to 0, because in this case we don't have any connection from the vertices to itself. But there might be some situations that we have some connection to itself also. Now the next node that we are going to continue is C. So from C we have a connection to A. So this means that we will update CA to 1. And then from C we have another connection to D. So we will update CD to 1 over here. Then we are continuing to the D. So in D vertex we have a connection to A. So this means that we will update DA to 1. Then we have a connection to DC. So we will update DC to 1. Then we have a connection to E. Then we will update DE to 1. And finally the last vertex is E. So we will check E. From E we have a connection to B. So EB will be 1. And from E we have another connection to D. And ED will be 1. So with this we have completed the representation of graph in this adjacency matrix. So here the cells represents the edge. We have initialized this matrix with 5 to 5 because we have only 5 vertices in our graph. Now with this we have finished representation of graph using adjacency matrix. So this is how it should be. Now the next method for representing a graph as adjacency list. So in this case we are using linked list to save all these links between the vertices. So to make this very clear, let's see this example over here one more time. So here we have a graph like this. So this is the graph that we represent in case of adjacency matrix. Now here we will represent same graph using adjacency list. So in this case, the first thing that we are going to do, instead of creating 5 to 5 two-dimensional array, we will create one-dimensional array with the size of 5. And then we will initialize all vertices to this array over here. Now you might be interested why we are creating one-dimensional array with the size of 5. So here we have 5 vertices, so we will initialize an array and we will insert all these vertices to this array over here. Now the next thing that we are going to do, we have to insert the edges between these vertices to this. Here for edges we will use linked list. So here we see that from A we have a connection to B. So this means that here we will create a linked list which is connected to A. So here it will be like this. And this shows that from A we have a connection to B. Then from A we have a connection to C. So this means that we will create another node and link it to B over here. Then from A we have a connection to D. One more time we will create a node and connect to the linked list that is located in the cell of A. So it will be connected to C over here. Now with this we can easily identify that from A we have a connection to B, we have a connection to C, and we have a connection to D. Now we will continue to the next vertex. The next vertex is B. So from B we have a connection to A and E. So this means that A and E will be added over here as a linked list, so they will link to B over here. So from here we can identify that from B connection to A and E. Then the next node is C. So from C we have a connection to A and D, so A and D will be created as a node and linked to C over here. So from here we can identify that we have a connection to A and D. Then we will continue to the next node is D. So from D we have 3 connections to A, to C, and to E. So all of them will be added here like this. So here we see that we have connections to A, to C. And finally the last vertex is E. So from E we have connection to B and D. So they will be added over here. Now this is how our graph is represented using adjacency list over here. So here the main point is we are storing the vertices in the array and the edges in the linked list. But in the first case we were using the array itself for storing the edges. Now you might be interested if we have 2 types of graph representation, which one we should use. So if the graph is complete graph, almost complete graph, then we should use adjacency matrix. On the other hand, if the number of edges are few, then we should use adjacency list. So let's look at these cases very closely. So if we have a complete graph, it means that we have the maximum number of edges possible in the graph. So in that case, all cells of this matrix will be filled. So we are using 2-dimensional array very efficiently. It means in this case we can use adjacency matrix. Now let's say we don't have enough edges in this graph over here. So this means that this is not optimum to use matrix here because most of cells will be empty. Hence, in those cases, we typically avoid the adjacency matrix representation. In this case, we are avoiding adjacency matrix representation, but we are using adjacency list because in this case, all edges are stored in the linked list. So depending on how many number of edges we have, we can increase or decrease the size of linked list over here. But in the first case, we don't have such option. Once we create 2-dimensional array, we cannot increase or decrease it. If the number of edges, it's better to use adjacency list representation. Now with this we have completed graph representation. So see you in the next lecture. Now in this lecture we will look at graph traversal. The graph can be traversed in 2 ways. The first traversal is BFC, which stands for breadth first search, and the second way of traversal is DFC, which stands for depth first search. So when we say graph traversal, we basically mean the process in which each vertex of graph is visited. Now let's say we have a graph like this, and the process of visiting each vertex is called traversal of the graph. Now in this graph we can easily see that to traverse all elements of it, we need to clearly define way to visit all elements of traversal. So when we are in this vertex over here, from here, which vertex we will visit? We can go to D or we can go to E. So to answer this question, we need a traversal method, which will help us to go further. Now, as we mentioned, we have 2 ways of traversal. So the first way is breadth first search, which is BFC in short. So we will look these methods one by one. So let's get started with BFC, which is breadth first search. So BFC is an algorithm for traversing graph data structure. So BFC starts at some arbitrary node of graph and explores the neighbor nodes first, before moving to the next level of neighbors. Now, let's say this is our graph and we want to traverse it using BFC. Here, as we mentioned, it's using level order traversal. So this is our first level, this is second level, and this is third level. So let's say if we start from A, first we have to visit first level elements, then we have to visit second level elements, then finally we have to visit third level nodes. So in this case, if we start from A, our traversal will look like this. We are visiting A, then B, then C, then D, then G, then E, and F. So as you see, first we are finishing visiting of first level, then we are continuing to visit second level elements, and then we are visiting third level elements. So from here you can easily see that BFC are traversing the nodes in a level order traversal. So First we finish the current level, then we continue to the next level. So it can be compared with the level or the traversal of tree. But here in case of graph, it's different from the tree, because in case of tree we don't have cycle, but in case of graph we have cycle. And this means that we might have a problem to visit nodes infinitely, because from A if we go to B, then C, D, and we can come back to the B, because here we have a cycle. Now to prevent these cases, we will have another Boolean value which will show that if this node is visited or not. So we will explain it in the algorithm of this BFC. Now here I've just shown you how the logic behind BFC is work. So hopefully you have understood the logic behind BFC. Now based on this logic, let's see how the algorithm of breadth first search method looks like. So basically we implement BFC for a graph in Python using queue data structure. Now if you look at this algorithm over here, we are starting with enqueuing any starting vertex. So we are enqueuing this starting vertex to the queue. Then while the queue is not empty, we are dequeuing this element and checking that if this is unvisited, we are marking it as visited. Then we are enqueuing all adjacent unvisited vertices of P to this queue over here. Now let's see how this is working in practice. So as a first step, if we start from A, so the first step is we will enqueue A to this queue over here. Now we are continuing to the next line. So in the next line it says that while queue is not empty, we will dequeue this element from here. So we see that queue is not empty, so we have one element over here. So if we dequeue it, A will come like this. So we have dequeued A from this queue over here. So now we are checking if A is unvisited. We see that it shows that it's unvisited now, so we are marking it as visited. Then we are enqueuing all adjacent unvisited vertices of A to this queue. Now in our case we marked A visited, and the adjacent vertices are B and C. So we are enqueuing B and C to this queue over here. Then we are continuing our loop. So in this case queue is not empty, so we are dequeuing the next element. So if we dequeue, the next element will be B. Now we have dequeued B and we are checking if this is unvisited. We see that it's unvisited, so we are marking it visited. Then we are adding all unvisited adjacents of B to this queue over here. Now here you just need to take into account that we are adding only unvisited vertices. So here for B we have 3 vertices, A, D and G, but in this case we are not enqueuing A because A is already visited, so we are enqueuing only D and G to this queue. Then in the next step, one more time we are continuing our loop. So queue is not empty, so we are continuing to dequeue the element. So if we dequeue element, it will be the C. So after dequeuing, we are checking that C is visited or not. So we see that C is not visited, so we are marking it visited and adding the unvisited adjacent vertices of C to this queue over here. So in our case it is E and D. So D is already here, so we are not adding D, so E will be added as the next element to this queue. Then we are continuing our loop. So when we dequeue the element, D will be dequeued, and we are continuing to D and see that D is unvisited, so we are marking it visited. Then we are adding unvisited adjacents of D. So in our case we have F here, so we are adding F to this queue and queuing F to this queue. Then we are continuing the next stage of our loop. So in this case queue is not empty, so we are dequeuing the next element. So the next element is G. So we are checking that if this is unvisited, so this is unvisited, so we are marking it as a visited based on this condition. Then we are enqueuing all adjacent unvisited vertices of G. So in our case it's F, so F is enqueued over here. Now then we will continue to the next element. So the next element is E. When we dequeue from the queue, we are seeing that E is dequeued, and then we are checking that if E is unvisited, so we mark it visited, and the adjacent unvisited vertex of E is added to this queue over here. Now we are continuing to the next stage. So in this case we see that queue is not empty, so we are dequeuing the element. So in our case it will be F, and then we are enqueuing all unvisited adjacent vertices of F to this queue. So in our case we see that all adjacent vertices of F are visited, so we don't have any unvisited vertices. So in this case, we are not queuing any element to this queue over here, but we are marking F as visited. Now in the next case, if we continue, we see that one more time we are dequeuing the F, but F is visited. So we will continue loop until all F's are dequeued from the queue over here. So at the end, our algorithm is finished. So all vertices of this graph are visited. So this is how breadth first search algorithm works. Now in this lecture, we have learned traversal of graph, and we have learned how can we traverse it using breadth first search algorithm. Alright, in the previous video, we have mentioned that there are two ways of traversal of graphs, which are breadth first search and depth first search. Now we have explained BFC in previous lecture. So in this lecture, we will talk about DFC. The formal definition of DFC is, it's an algorithm for traversing a graph data structure which starts selecting some arbitrary node and explores as far as possible along each edge before backtracking. So you see that we have a contrasting difference between BFC and DFC. In DFC, we are going as deep as possible using given edge, and once we have reached the bottom, then we do the backtracking. Now let's say we have a graph like this, and we want to traverse through this graph using DFC. So according to our definition, we will start from some arbitrary node and we will go as deep as possible. Then we will do backtracking. So in this case, if we start from A, then the next node will be C. Then we will continue with E. Then from E, we will start to backtracking F, D, and B. Then once we reach the top, then we will go as deep as possible again. So this is the order in case of DFC traversal. But in case of BFC traversal, we were first traversing all neighbor nodes, then we were going to the next level. Now you see that BFC and DFC algorithms are very different. Now based on this logic, let's see how the algorithm of DFC works. Now this is our algorithm. So as you remember, in case of BFC, we were using queue in our algorithm, but in case of depth first search, we are using stack. Because for this case, stack functionality is very useful. Now the algorithm starts with any arbitrary node and saying that push any starting vertex to this stack over here. Now if we start from A, we are pushing A to this stack over here. Now in the next step, we are popping element from this stack. So we know that when we pop the element from the stack, it brings us the last element from the stack. Now in this case, we have only one element, so it will pop out A from here. Then we are checking if A visited or not. So we see that A is not visited, so we will mark it as visited. This sign shows that this is visited. Then we will push all adjacent unvisited vertices of A to this stack over here. Now here we see that A has two adjacent vertices and both of them are unvisited. So we will push these vertices to this stack over here. Now, after pushing it, our first stage of loop is finished. Then we will continue to the loop again. So here it says that while stack is not empty. So we see that this stack is not empty. So we will pop out element from the stack. So here we know that according to the functionality of stack, it will pop the last element. So C will come out. So then we will check that if C is visited or not. So we see that C is not visited, so we will mark C as visited. Then we will push all adjacent unvisited vertices of C to this stack over here. So we see that in our case, we have D and E. So we will push D and E to our stack over here. Now, after pushing it, we are continuing to the next stage of loop. So in this case, one more time, we are checking and seeing that our stack is not empty. So we will pop elements. So in this case, the last element is E. E will come out and we see that E is not visited. So we will mark E as visited. Then we will push all adjacent unvisited vertices of E to this stack over here. So in this case, we have only F here. So in this case, for E, we have two adjacent vertices, but C is already visited. So that's why we are not going to push it here, but F is not visited. So we will push F to this stack over here. Now in the next stage, one more time we will pop an element from here. So the last element is F. So this means that F will pop out and we will check that f is not visited, so we will put it as it visited. Then we will push all adjusted unvisited vertices of f to this stack over here. Now in this case we have d and g, so we will push them in our stack. So one more time, then we will call pop method. So pop method will bring us the last element from the stack. So the last element is d. So we will check that if this is visited or not. So we see that d is not visited, so we will mark it as visited. Then we will add adjusted unvisited vertices of d to this stack over here. Now in this case we see that we have two adjacent vertices of d, but c is visited, so we will add only b. So then one more time we will call pop method because our stack is not empty, so b will come out. Then we will mark b as visited. Then we will add adjacent vertices of b to this stack over here. Now in this case we have three vertices, a, d, g, but a and d are visited, so we are not going to push it to this stack. We will push only g. Then one more time we are checking that stack is not empty, so g will come out because this is the last element in our stack. Then we will check that if g is visited or not. So we see that g is not visited, so we will mark it as visited. Then we will push all adjacent unvisited vertices of g to this stack. Now we see that all adjacent vertices of g are visited, so we are not going to push any element to this stack over here. Now our loop still will continue because here you see that we have g, d, b elements over here. Now one more time we are calling pop method, so in this case g will come out. So we will see that g is visited, so we will not do anything and we will continue to the next stage of loop. So here one more time if we run pop method, d will come out, and if we check d we see that d is visited, so we will not do anything, so we will continue to the next stage of loop. Now here we see that we have only one element, so in this case b will come out and we will check b is visited, so we will not do anything for this part over here. At the end, after b, we see that all elements of stack are popped out, so the stack is empty, so this means that our algorithm will stop here. So if you see the order, we start from A, C, E, F, D, B, and G. So it works the way that depth search algorithm should be. Now with this we have completed explanation of depth first search algorithm, and we did dry run for DFC. So see you in the next lecture. Alright, in this video we are going to talk about difference between BFC and DFC. So let's look at them one by one. So let's imagine that we have a graph like this and we want to traverse through this graph using BFC method. So in case of BFC method, we know that it looks like a level order traversal. So this is our first level, this is our second level, and this is our third level. So in this case, first we need to visit all elements in the first level, then we are continuing to the second level, visiting all elements of the second level, and then we are continuing to the third level and visiting all elements of third level. Now in this case, if we traverse through this graph using BFC method, the traversal order will be like this. First it comes from A, then B, then C, then D, then G, and E, F. So as you see, BFC method visit first the neighbor nodes, then continue to the next levels node. Now if we do the DFC traversal for same graph, it's going to be look like this. In this case, the traversal goes as deep as possible, then visiting all deepest nodes. Then after visiting them, we are doing backtracking. Then when we reach the top vertex, then we are continuing as deep as possible one more time. Now in this case, if we start the traversal, it will start from A, then continue to the C and E. It goes as deep as possible. Then from E, it starts to do backtracking. Then it comes, then from here, it will continue again deep as possible. So if there would be an element after G, it will continue to the G, then come again as a backtracking. Now from these two pictures, you can easily identify the difference between them. In case of BFC, it visits first neighbor nodes. In case of DFC, it goes as deep as possible. Now let's see in this table the differences between them. So based on this criteria, we can identify the difference between them. So the first one is, how does it internally work? So in case of BFC, we said that it goes in breadth first. So this means that it visits first neighbor nodes, then continue to the next level. But in case of DFC, it goes in depth first. So this means that it visits first deep nodes, then come back. Now we know that when we implement these algorithms, we are using another data structures. So in case of BFC, we are using queue, but in case of DFC, we are using stack when we are creating these algorithms. Now the time complexity for both method is OV plus E, because in this case, we are visiting all vertices and edges of graph. So that's why V is the number of vertices and E is the number of edge. So in this case, it is OV plus E time complexity. Now the space complexity is also OV plus E, because in this case we have to insert all vertices and edges to the memory by using queue or stack. So that's why for both cases space complexity will take OV plus E. Now the main point over here is when we can use BFC or DFC. Generally, and DFC methods are using to search in a graph. So if you are searching for a node and we know that that target vertex is located near to the starting point, then we can use BFC. But if we know that the vertex that we are searching is located as deep as possible, then in this case we will use DFC. So these are the main differences between the BFC and DFC methods in case of graph traversal. Now with this we have completed graph traversal. So see you in the next lecture. Dijkstra's algorithm. Dijkstra's algorithm is an algorithm used to find shortest path between points on graph. Let's look at it in the action. To start, each point's initial cost value is set. The starting point is set to 0 and all others are set to infinity. We start from the first point, which is A. Starting at the present location, we search for unexplored points. Once found, these points become candidates for the next move. In this case, B and C are our candidates. The cost of each point is calculated. The method of calculation is current method's cost plus the cost of moving to the candidate method. So in our case, the cost for B is going to be 2, because 0 plus 2 is 2, and the cost for C will be 5, because the cost of A is 0 and plus 5 is going to be 5. So if the calculated cost is less than the current value, the points cost is updated to the new value. So in our case, our calculated cost for B is 2 and for C is 5. So both of them are less than infinity number. That's why we updated their cost here. For the move, we choose the one with the lowest cost. In this case, it's going to be B. At this point, we have determined that chosen path A to B is the shortest path from the starting point to B. The reason for this is that choosing another point, which is AC, requires high cost than our current path. Taking the path determined to be the shortest, we move to the point B. From B, there are 3 candidates, C, D, and E, and they are added as new candidates. Using the same method as before, we calculate the cost of each candidate. So the total cost of moving from B to C is 2 plus 6, which is 8. As we said before, if the calculated cost is higher than the current value, we are not updating it. If it is less than, then we are updating. In this case, 8 is greater than 5, so we are not going to update C's value. C remains in 5. The cost of remaining points D and E are updated. From the candidate points, we choose the one with lowest cost. In this case, it is D. Because the cost for E is 5 and the cost for C is 5 and the lowest value is D. So we are moving to D. At this point, we have determined that the chosen path A, B, D is the shortest path from starting point A to D. And this is the path with lowest cost. Thus, we know that passing through any other point to get to the D is certain to have a higher cost. In this way, Dijkstra's algorithm searches through a graph, determining shortest path to each point, one point path at a time. So the same operation is repeated until the last point, G. From the point D, we have only one path, and the cost for this path is calculated. 3 plus 4 is going to be 7, but we have a current value which is less than the 7, so we are not updating it. In this case, from D to E, as we calculated, it's 7, so we are looking for minimum value. The minimum value for our path will be 5. From C, we have only one path, and the cost for this path will be 13. And as we have another point with less cost, which is E, we will continue from the E. As we see, we have only one path from E to G, so with using same method we will calculate cost. And 5 plus 9 is equal to 14. And when we compare this path to this path F, we see that 13 is less than 14, so we'll continue from here. From F to G, the cost is 13 plus 7 is equal to 20, which is greater than 14. And this means that the path from E to G is better than the path from F to G. And finally, we reach our goal, and the best way is A, B, E, G with cost of 14. And as you can see, Diecastr's algorithm efficiently searches for the shortest path by devising which point to choose next. Advantages and disadvantages of Diecastr's algorithm. Advantage: it is used in maps to find shortest path. For example, in Google Maps, they use Diecastr's algorithm. Distance between location refers to the edge. It's used in telephone network as well. And disadvantages: it cannot handle negative edge. It does blind search, so the waste of a lot of